Thanks everyone for joining us today, if you're here today, and thanks for those who will watch the recordings later. But without further ado, I would like to hand it over to Dr. Tom, talking about climate science and how we can all get involved. Thanks, Tom. Hand it over to you.
Yeah, no worries. Okay, so I'll just share my screen. And okay, so I've got a whole bunch of different things that I do in my life. And one of the ones that I'm trying to spin up now is Southern Ocean Carbon with some other directors, which is all about trying to grow seaweeds to sequester atmospheric carbon. And the reason that I want to do this is because for my job, I spend my whole life telling people about how the world's going to burn because of climate change. And I wanted to stop just being the harbinger of doom and start trying to actually implement some of those solutions so that we actually can try and prevent some of those things from actually happening in the first instance. And so this presentation is about why I believe this is the solution, a solution, and why that makes sense. And then at the end of this presentation, very happy to just field questions in any questions you have, really. How I came to actually get to this position, can be really, really broad and kind of off topic. I don't really mind, but this is more of here's why we want to do this. So the situation is carbon dioxide is warming the planet, and we know that this is happening. We've got ice core records that have been reconstructed that go back 800,000 years. They show a really strong relationship between carbon dioxide and temperature. And it's also been demonstrated that it's the carbon dioxide that goes up first and that temperature follows. So we know that the carbon dioxide concentrations are a driver of heat, of the increased heat capacity of the atmosphere. And that's what warms the planet. And we're now well above. Can you see my? Just put a thumbs up, Claudette. Can you see my cursor? Yep. We're well above the paleo record maximum concentrations of carbon dioxide. And if we increase the temperatures as much as that, here we're looking at a 6 degree warmer world following this kind of relationship, and that's pretty scary. It takes a long time to get to that, so thousands of years for that to stabilize at that level, but certainly hundreds. But what we're doing at the moment is just this releasing, in some ways, a carbon bomb into the atmosphere, which is then increasing the heat substantially. We can see on this plot on the right-hand side, which is a recent release from the IPCC, that when we use simulations of the Earth's climate system, we can really well represent what's been happening in the historical period from about 1850 onwards, depending on where you are. And we cannot reproduce this observed trend without including human-induced factors into the climate system. So when we just use natural only, it just putters along at normal levels. So this is what tells us, and I've got a whole nother presentation that goes into this. This is what tells us that it is humans that are warming the planet, and we're doing it by burning fossil fuels. Now, the biggest issue that we've got here is actually that we're releasing too much CO2 into the atmosphere, and we're not removing enough CO2 from the atmosphere. So it's really important for us to stop releasing any, but it's also really important for us to remove the additional that we've already put in there. This is another release from the IPCC report. So that's the Intergovernmental Panel on Climate Change. They are a group of scientists who look at all of the published research. They don't do any research themselves, well, not for this job. They do research for the rest of their jobs, but this particular job is looking at all the research that's been published and say, given that this is what we know in the published arena, what can we say about climate change and how the climate system works? And so here we can see the historical warming trend, and then that overlaps slightly with the projections. And we can see here that for every single ton of carbon dioxide that we release into the atmosphere, there is a known amount of climate warming that we should expect. The relationship is linear. This means we just want to stop putting carbon into the atmosphere and we need to take it out. Now, at present, this amount that we've already released from basically the 1800s to now is the equivalent to 2 Amazon rainforests worth of carbon released into the atmosphere. And to give you just a spatial recognition of how much that is, that's almost the whole of Australia covered in forest, twice burnt and put into the atmosphere. That's what we've done with all the fossil fuels we've burnt to date. That gives you a sense of the scale of the problem if we want to try and grow more trees. We'd have to grow the entire of Australia covered in really dense, deep, sort of 50 to 100 metre rainforest, which we can't do because we don't have enough water. There's the central of Australia is a desert because there's no water there. And we can't do it over the rest of the planet as well. And plus, we can't grow trees where we need to grow food. So we've got a really big problem in terms of where we can actually grow trees and the scale at which we can do that on a terrestrial sense. And I think it's really important to understand that scale of the problem. So then if we know that we've got all this carbon dioxide in the atmosphere and we need to share it, to store it somewhere, well, then where can we store it? And this is a really good example here. We've got 820 units sitting in the atmosphere. To give you a sense, all of the vegetation on Earth is currently 600 units. So we're saying that we need to more than double the amount of vegetation on the entire, on the terrestrial space. And we know that that's also at risk of burning down. So although it might be a really good thing, we do need to massively increase the size of our forests. Because we're destroying so much habitat for so many organisms. It's not going to be enough to actually solve the carbon dioxide problem in the atmosphere. So we need to look at other places we can put it. Now, the surface ocean is 900. It's kind of a similar sort of size, similar magnitude. But we also, and I'll get to how long does it actually stay in each one of these different parts of the system. The deep ocean has heaps of carbon in it. So actually putting an extra, say, half of the units that are currently in the atmosphere, let's say 400 down into the deep ocean, it wouldn't even notice. There's so much there. And that's a really similar thing in soils, in rocks and sediments. The problem is that actually all the carbon that is currently stored in the ocean is basically the same volume that we've currently got stored in fossil fuels. Now, I'm not sure if that's taking into account from the 1800s onwards, where did they start that number from? But you can see it's a really big number, right? If we burnt all of this and basically put it all into the atmosphere, that would be devastating to the planet. It would really be a big problem. So we've got to keep all that in the ground and stop using it. So this gives you a sense of sort of where all the carbon currently sits and therefore where it would be easiest to try and put it back into. And of all of these, rocks and sediments is one of the solutions, soils is one of the solutions, and the deep ocean is one of the solutions. Oh, I thought there was another slide there. Maybe nope, I've skipped one. Here we go. Yep. So we've got this, the soils is one solution. Let's look at that first. In each one of these this figure here talks about how long does carbon stay in each one of these different parts of the system. And in order to sequester, so we have kind of these standing stocks of carbon that are sitting in the system. And then and standing stocks is what I like to think of, if it's in there for less than 100 years, then it's just a stock. It's like transient. It goes into a tree for a little bit and then it kind of is released back into the atmospheric system again. So the more we can have, the larger we can make these standing stocks, the more forests we have, the more productivity we have in the surface ocean. That's really good in the immediate term. That would have an immediate effect of taking carbon out of the atmosphere. But it would basically start getting released again in about 10 to 100 years, depending on which option, as you can see here. So we can put stuff into the soil, and that's really good, but then it's going to come back out again soon, like soon from biogeochemist point of view. And similar in the surface ocean, if we just focus on productivity in those areas there, and the surface ocean is the top 100 meters. So you could argue it's the top 1,000 meters, doesn't really matter too much, but it's that really, the top layer of the ocean. The ocean's 4,000 meters deep, so the top 100 meters isn't that much. So this is good. Let's try and increase the amount of ecosystems we have in both of those spaces, but we've got to recognize that that's not going to be a long-term solution for carbon. What we back into the system. And similar with just actually dissolved inorganic carbon in the ocean itself, if we put it into the right places, which is less than 1,000 meters or deeper than 1,000 meters, and in specific spots, then we can actually we've got such a main place that it's no longer a problem anyway if it comes back up. But it's key to understand that in order for it to be a sequestration method, you need to be looking at the 1,000-year time scale. So we need to be taking this out. So it more or less just is like it's inert. It is not reactive. We're getting it completely out of the system. And that's the hard bit. So in order for us to get these solutions happening, first thing, we have to get emissions down. We have to stop emitting. We have to have transport that doesn't rely on fossil fuels. We have to have energy production that doesn't rely on fossil fuels. And we know it can be done. I'm in Tasmania. We've been running on hydro here forever. It was actually pretty much the first energy production system they set up down here. And so hydroelectric is an excellent renewable source. When it's coupled with things like wind and solar, it works really, really well as a battery. So it can be done. Now, Tasmania has particular natural assets that are not available to everybody else, but it's proof of the fact that a whole jurisdiction, a whole region can actually be running effectively at carbon neutral. And so it's possible. Now, there's lots of other solutions I wanted to mention. So there's direct air capture and storage. So this is where there's particular technology. It's quite expensive to build. It's quite expensive to run in terms of energy, but there's direct air capture. You actually have these filters that effectively you pump water through it. It absorbs all the carbon, gets the carbon out of the atmosphere that way. And they have lots of different ways that they then store that long term, be that turning it into a solid or capturing it as a gas and pumping that gas down into somewhere else, which is out of the way. There are also rock solutions. These are pretty interesting. One is using the rock solutions to change the acidity of the entire ocean. So this is where you're dumping huge volumes of rock that then dissolves into the ocean. That then changes the pH, which allows the ocean to suck up more carbon. Now, all of these things have huge problems associated with them, but I wanted to make sure I mentioned that these are things people are looking at. And if you look at the actual volume of rock and the volume of carbon that's stored in rock, those types of solutions are attractive because of the scale that they can achieve. There's also ideas of pumping water that's really, really rich in carbon dioxide down into the deep basalt rocks, and then it actually creates a solid. It reacts with the basalt rocks and creates a solid down deep in the lithosphere, and it gets it out that way. And so these things are possible. It's all a matter of how expensive they are and whereabouts can you do them, how easily achievable is it. Fertilizing the ocean is one of the things I did my PhD on. It absolutely works. Except it requires us to dump fertilizer of various sorts into the ocean in order for marine microalgae to then have huge blooms. Those blooms, then you need to encourage them to aggregate and sink to the bottom of the ocean as quickly as possible. as I mentioned before let's see if I can go backwards. Here we go. If we're only sitting in this top surface layer, it gets released in the same season. So you really need to get that growth to happen in this top layer here and sink down into these deep ocean layers or even to the sediment in order for it to be effective. That's the bit that's really hard. And it's really hard to measure. It's really hard to prove that it's working. And it basically is kind of, a lot of these problems are saying, well, we've got to suck carbon out of the atmosphere, but all these things actually give the big emitters a reason to say, oh yeah, it'll be okay. We'll sequester carbon, and therefore we can keep burning the fossil fuels. We have to actually doing both, and this is one of the biggest issues. Biochar is also an excellent solution. It's one of the ones that Southern Ocean Carbon are focusing on, and we're doing that because of the immediate term, where biochar allows us to take organic material, turn it into something that's very close to inert, and then put it somewhere sensible, like in the soils. And this is that idea of where if we can increase the standing stock sitting inside this region here, then it buys us time. It's not the best solution, but it's a very good immediate solution. We know it works. It's easy to do. We can create it using green energy sources. So it's really good to take the biological material, cook it until it basically turns into just the carbon, which is very inert, and then spread that through the rest through that environment. Bioenergy is another example where we grow stuff that then we cook or we burn to then create the energy. So that sort of ends up in a circular cycle. It sucks up the carbon, we then burn it, releases the carbon. So there's it is a closed system. Again, it's and then if you then can keep the carbon dioxide, instead of it being this sort of circular system, like grow a forest, burn the forest for energy, and repeat that system. If you can actually capture the carbon dioxide that's coming out and bury that, it's sort of sitting in this, it aligns with this direct air capture kind of method. But it's about thinking about things a little bit more in a systemic way. And then you've got the really big ones. Afforestation, which is growing forests where there wasn't one. Reforestation, growing forests where there used to be one. And this kind of sits a little bit alongside the carbon farming and growing other types of vegetation sources. And this is where we sit in this. Our idea is other vegetation. So let's look at the ocean. Let's try and grow vegetation there, and let's see where that fits. So seaweed as a sink. There are people have been looking at this for some time now. And it's worthwhile recognizing that growing seaweed is one of the largest agricultural or maricultural activities on the planet. The Japanese and the Chinese have been eating seaweed for literally thousands of years. And so they have big industrial solutions on how to actually grow seaweed up there. And that means we know how to do it really well. It's not like it's a brand new technology. So this is one of the things that I really like about it. Now, there's lots of different ways that you can grow seaweed. You can do it in shallow water, which is typically what they do when they want to grow it for food and for other techniques, because it's heaps easier to get access to it. But what you need to do if you're going to grow seaweed to try and sequester carbon is you need to grow it in places where the carbon, the seaweed itself can actually get sunk to the deep ocean really easily. So there's lots of ideas of how the different platforms can take place or what they can look like. Sorry, some of the figures haven't come through very well here. Here's one in the Sargasso Sea. It's a massive area in the Pacific, and it's about growing big mats of seaweed that then sinks down to the bottom of the ocean. And you can't see here, but it's saying that it doesn't get released back into the atmosphere for sort of 100 to 1,000 years. So that's a good sort of example of what's going on there. You can increase the amount of nutrients in the location, and then the microalgae bloom. They then sink to the bottom as well. You've got more sort of systems where they're growing large scale sugar kelp, which hangs down, which is why those ones are drawn that way. And then you can use that to cut that off and let that sink to the bottom. And then so it's a similar system, but you can see there's lots of different types of platforms, but more or less you're talking about putting rope in the ocean, growing seaweeds of various kinds on them, and using that biological material to explicitly capture and sink down to the deep ocean. Here's a macrocystis version. This is a macrocystis version as well. It grows to up to 100 meters, and it can grow, a really well-developed plant can actually grow 100 meters in a single year. That is where the actual huge amount of potential to sequester rapidly really starts to, the potential is what we're excited about. And that's what we're looking at as our organization. How can we promote the production of macrocystis forests in places where they used to be? How can we promote the production of macrocystis in offshore environments where we can sink it to depth? Both of those things are things we're really excited about trying to do. And you see here, there's sort of lots of thoughts about doing the growing of seaweeds, lots of different kinds of seaweeds in combination with other marine activities, which was presented in the Blue Economy CRC presentations for those that are interested in those. So that's the theoretical examples, but what does it actually look like? So the Chinese, this is an example from the Chinese here. They have a floating platform that generates the energy to run a pump. The pump then pumps air down to the deeper part of the ocean. That pumping the air down to the deep ocean then is put into a pipe that then, like the air gets put into a separate pipe that then pushes up, that then sucks the deep water up, which then creates the nutrient flow to encourage more rapid growth of the seaweed. This particular paper was published in 2020. It's a successful activity. They can see how that would work. There's lots of problems that are associated with forcing the upwelling of deep waters to the surface. That the science is, you might hear people saying that the science hasn't yet been settled on growing seaweed in the ocean for sequestration methods. And it really comes down to the method that you choose. So here we've got sugar kelp being grown off the coast of North America. They use lots of different types of activity, different sort of formats. Here we've got some ulva being grown, and this is more in sort of those environments where they're just doing it for human consumption, and be it in cosmetics and the like. And I thought I'd also put in over here the fact that this is how they actually grow the kelp out in the system. So you have pipes that are wrapped in a special twine that the algae likes to grab onto. You make sure that the algal twine gets exposed to the baby kelp that then grab a hold. You then grow them out in the lab, and then you deploy those out onto ropes. You run the rope through the pipe, and then the twine goes off around the outside of it as it sort of unspools. And these systems can either be in these upright sort of situations, or they can be lay flat environments. But there's lots of different types of systems people have used for growing these. And we're setting up a system more similar to this one here at Newtown High School in Tasmania, working with the year 11 and 12 students there as part of their various different projects. So some of them are doing engineering and design projects, some are doing agriculture and projects. And so we're getting the kids to try and really get their hands dirty, as it were, doing some real work on that. And so we're finishing the first cohort of year 11s coming through this year. They'll be finishing in a couple of months. So what have we been doing? We've been done our first number of deployments, testing sort of what kind of biofouling do we need to worry about, what kind of communities are there, how can we promote the right kinds of species in those communities, working around a lot of those practical challenges of how you actually go about deploying ropes in the ocean, what's the stresses they need to put up with, what kind of flotations required to make sure that all these things actually work, and how do we promote the right kinds of species that become structural species that we can use for supporting other environmental co-benefits, such as creating new ecosystems for other organisms to come in and share in that space. But yeah, we're out there and working on that in the Tassie waters already. So I really wanted to keep my talk about this as limited as possible, so that we could talk more about with the students about what it is that you found useful, or what are the questions you have about getting involved in this kind of industry. What was my pathway to get here and the like. So please, if you would like to ask questions, I'm here to answer and sort of provide, I guess, my perspective on that.
While we wait for some questions, I actually have a couple to kick us off.
Go for it.
So for everyone who's just joined, my name's Claudette. I run Ocean Youth, which is a program that's about building the capacity of young people to influence positive change for the ocean. Now, this is a hugely fast-growing area, actually. I find the whole seaweed, algae industry and the growth of it really, really exciting. What kinds of careers or pathways, like this industry is going to create jobs, probably, well, it is starting to create jobs in the next 5 or so years. What kinds of jobs do you see starting to be created, and what might be some of the pathways to get there?
Yep. So there's a bunch of sort of just understanding the biology of the system. So doing sort of marine biology, or in this particular instance, marine botany, is actually a really useful sort of skill set to have. There aren't that many people that do understand a lot about seaweeds, which is interesting, even though it's such an enormous central part of the marine ecosystem. So that's, I guess, the first one to start with. Then there's actually the idea of mariculture. So how do you actually do agricultural production in the ocean? That's something that is quite new. There's a lot to learn about that. There's a lot of land-based techniques that can be translated. It's, in all of these cases, it's about finding systems. How do you build a really efficient system so that you're not wasting time either doing a low value activity all the time, like, spooling on the rope yourself? How do you actually build systems that actually allow that to be automated, industrialized, that kind of thing? Now, industrialization is often a really bad word, but I actually see it as something that is crucial for us to achieve the carbon sequestration efforts that we're going to have to do into the future. We have got to this point because of industrialization. It is because humans are really, really good at saying, I want to do this one thing, and here's the way to do that as efficiently as possible. That's the way I kind of think about industrialization. We need to do the same thing in the carbon sequestration effort. How do we actually get this to the point where it's sequestering as efficiently as possible? And so it's about although industrialization can be a dirty word, it's about reframing how you actually think about that. And there's, it could be a dirty word. Growing seaweed could actually be a really bad solution if done in the wrong way. So it's about figuring out, okay, if that's our goal, sequester carbon, how can we do that in the most efficient way? Now, what else do you need to do? You'll need to, what are the types of people we're going to need in this industry? We're going to need lots of engineers, marine designers, marine shipbuilders, ship designers, that kind of thing. Marine engineering is going to be a really big one for this industry. There's also we're going to need people that are actually out there on the water. So people who are working in the merchant navy. So people that are good at getting out on boats, really understand how to move ropes around. I've been out at sea. I've been down to Antarctica doing research in Southern Ocean, doing research voyages before I started my PhD. It's a really important part of understanding how to work safely at sea is really, really important. And people who are expert in understanding how to drive ships, so captains, run their engines. So that's a different kind of marine engineer. That's effectively a mechanic who works on the ship, but oh my goodness, are they amazing people? Those engineers. If anyone follows Star Trek, you see how good the engineers are. Well, that's what they're like on the ships at sea. They are amazing, amazing people. Then there's even stewards and people that actually sort of, chefs who work at sea and do that kind of work as well. So there's a huge array of things just inside that merchant navy bucket that will be needed as well. So I'm just looking at some of these questions coming in.
Yep. Clarine Wan Ling Hong has got.
So in terms of, I think conservation, the way that I see conservation is it's good if you want to do really small things, but you can't do conservation at broad scale with those small efforts. They're really, really good, and it's great to support those efforts, but we've got to figure out new models that allow those things to become commercially viable entities in and of themselves, where they're producing something that the market needs that allows the money to flow in so they can get to the scale they need to in order to, rescue our forests from deforestation, provide the kind of effort we need to make sure that those reforestation efforts are diverse and they've got a huge number of different species living inside them so that they actually are doing the job we're after. So yes, you can donate. That's great. It's great to get things started. But I think that whole idea of conservation, to me, is something that we need to conserve what we haven't already destroyed. So we need to just stop cutting things down. We need to stop destroying what's been lost. But then we need to shift our focus on agriculture, and in this case, mariculture, to say, how can we use the agriculture and mariculture as a way of being regenerative? So the things that we are doing are actually better in the environment than what we were doing before or what was already there in the past. And so one of my really big focuses for the idea of growing seaweed is that a lot of these areas that are in the open ocean they're just open deserts. There's almost no food there. There's no ecosystem. There's no structure. The animals that are out there are typically moving very rapidly from a reef to another reef, or those types of things. They're moving from one place of large productivity to another place of large productivity, and they just swim straight through those other areas. They're not really feeding or anything while they're there. If we can encourage those areas to actually have more ecosystems a part of them, then that actually means we're increasing the capacity of the ocean to support life. And we've got to approach things, I think, a bit more like that. In terms of the research area, what I'm hoping will start to happen more is actually the commercial sector will start realizing the value of research and actually start being those that are driving a bit more of that effort, particularly in this space of agriculture, mariculture space, and that is happening right now.
Just on the funding question, Tom, do you think carbon credits and the whole move towards carbon offsets will help improve the funding of projects like this?
I hope so. That's exactly what we're aiming for. I think we have to have carbon credits. We have to have carbon trading. We've demonstrated it's an excellent way of getting the commercial sector to engage in a particular type of activity. It was really, really effective when we did it for sulfur. So when we had acid rain over Europe, they implemented a sulfur trading scheme that within 2 years, they pulled all of the acid rain out of Europe. I think it was something like that. It was ridiculously quick. It was so effective. The difference was that sulfur was something that they were able to clean up out of their emissions far more easily than carbon. And so that was one of the reasons why it worked, where carbon has been less easily adopted or has had less impact. But I think those trading schemes had demonstrated that they're a fantastic way of getting the market to engage properly in solving a problem. And it's about getting the market to solve the problem. They're the producers of the problem. And we've got to recognize we're all part of the market. It's not just the big end of town. You know, we all drive our cars. We all like to go on our holidays. We all like to buy particular foods. And as a result, we need to recognize we're all part of that market. So how can we help that market and encourage that market to shift? And that's where we have to, what can each individual do? Well, vote with your wallet, go and find the organizations that are doing the right thing and support them. So funnily enough, was Seaweed always what I wanted to work with? Absolutely not. However, my wife, who you might have seen just walk past behind me, she is a marine botanist and always studied it just because it was really interesting. And she's astonished that it's now turning into something where there's an industry. And I think that's a really great example of how you shouldn't be trying to get educated for a job. You should be educating yourself in the things you find really interesting, and always being a bit open-minded about where you might end up applying those skills. But I'm a big believer in you should really be just focusing on those you really enjoy. If we kind of flip that and say, why am I studying? Why am I here? What am I doing? How did I start studying this? I didn't learn about oceanography until second year university. And then when I went through that course, everybody else was saying, this sucks. It's so complicated. It's all these systems and loops that impact on each other. And I was like, yeah, I know. I love it. I get it. It's so good. And that was where I realized that this is something I should really try and put my energy into, because I was able to think that way. It was something that suited me and it didn't suit others. And so that's why I got into oceanography. I then, when you're in the oceanography space, there's another area that's even more challenging, which is biogeochemical oceanography. And I really liked that too. So I went into that space and really enjoyed that process. And so I'm here because I started off following what it is I really loved. And then that has taken me from understanding the climate system from a fundamental point of view to then saying, hang on, how is the climate changing? How can I start trying to be someone that goes out and tells organizations, here's how climate change is going to impact your business, is going to impact what you're doing. So here's what you should be doing to try and encourage change. And then I've stepped sort of sideways a bit and said, right, well, how can I be part of that solution? And that's where I see Seaweed being a solution because of my training. I saw the movie 2040. I saw Dr. Brian on the movie, and I just went, he's right, that it'll absolutely work. We've just got to scale it. We've got to get it effectively in every area around the world so that we actually reach the scale to suck up the problem, basically. So that's, you know, the question is, how did I always want to work on Seaweed? No, but actually that's how I've got here. And that's why I'm doing this. Where are you going to target? Okay, so our target areas are there's currently a couple of test sites that are going to be popping up. There's going to be one that's more or less in the mouth of the Derwent River in Hobart. That's going to be very small. So in terms of impact on marine animals is going to be really minimal. There's also a lot of work that's been done on what kind of spacing do you need in order to make sure that marine animals just don't get tangled in it at all. And that happens to be 4 meters. So as long as we meet those, well, we're actually going to structure everything around 5 meter grids so that there's an additional space. So that's one for the big animals. You have to be quite big in order for 4 meters to start being a problem. So that's one way that we deal with that. Then as we go offshore, we'll just be following similar rules. And actually one of the biggest things, one of the ideas I've always had is when you're out in the ocean, I used to deploy things down into the deep ocean. Deep ocean's 4 kilometers deep. And so you'd have 4,000 meters of wire running out behind the ship because there's the space. You just run it out. And so the way I think about it is you don't even necessarily need to have grids. You could just have single lines that just go for a really, really long time. And the animals often can just swim around them. They don't get tangled in a single line like that. So that's there's lots and lots of different ways you can implement things at different scales as you move out to make it actually work. And that's why we're engaging with the Blue Economy CRC to make sure that the right types of expertise is looking at all these problems from all these different angles to make sure that if it's identified as a problem, then we engineer that problem away so that it's no longer something that is at risk to the marine environment. Oh, do you face difficulties doing research? Like, research is literally problem solving. So difficulties is like every day. You don't hear a lot of, you don't hear researchers say it very often, but basically we spend our whole life being wrong. So when I try and solve a problem, I come up with an idea. I say, right, let's test if that idea is right. You do some work. Doing some work could end up being 6 months of effort. It's often a very long time to figure out if you're right or not. But then you find out, no, that question, I was wrong. No, okay, throw that away. Well, you don't throw it away. You just go, right, well, we won't try that again. We'll try something else. And so research takes a long time because it takes a long time to figure out you're wrong. And so it's all about building those systems that make sure you fail fast. How can you prove that something is wrong as quickly as possible so you can move on to the finding out what the thing is that's right? And so then when you do find something that's right, you're pretty excited. And so that's why you write a paper and tell everyone about it, because it takes a long time to do that. So yes, lots of difficulties. As a researcher, the difficulties are enormous. The environment that you're working in is really challenging. From a physical point of view, if you're actually out at sea, not to mention the sort of structural point of view of working at a university. The funding systems are really, really challenging. Our systems are not well designed for that. I would not be encouraging anyone to aim to be a researcher. I would say aim to be something else first, and then if you really, really sort of find that useful, then go into that space, because it's really, really competitive, challenging environment being a researcher. However, you can do a lot of really cool stuff before you get to that research step. And a lot of people absolutely love the roles that they do after they finish their degree, and they go and they actually get to do the research every day, maybe under the guidance of a head researcher who has all the stresses, but they just actually get to do all the fun stuff. And I absolutely preferred my roles as a technician to the roles that I've had to step into to make a difference. So yeah, how do you solve them? Every problem's different, but basically you just have to be really positive. You have to keep sort of going, okay, well, that didn't work. Let's try again. You have to build up a lot of mental resilience to be a good researcher and to work in this space. And I'd say that's true also of starting a new business and getting through your degree and all that kind of stuff. The hardest year of my life in academia was actually doing my honours year. And then after that, it was so challenging that actually it made some of the other things a bit easier to handle because it was so hard. But I could have made it easier on myself by doing more work earlier on in the year. So front load your effort. So yeah, I think
Tom, that's all a fantastic advice. I have a question about the Year 11 project that you said you were doing with one of the schools. Yep. There. I think it's a pilot study. What are you actually doing with that school, and is there a way that we might be able to replicate it elsewhere?
So yeah, so the whole idea at the moment is to try and spin up that as I'm recognizing that we're across the whole country. So, but basically a Year 11 and 12 subject that could be rolled out to many other areas. There's a certain level of expertise and infrastructure that's required in order for it to be done, but we're trying to build it in a way that's modular and then be able to reach out to those schools and those regions where it's an appropriate thing to actually encourage people to do. You know, it's not a sensible thing to do in the centre of inland New South Wales, for example, but So there's a number of things boxes you need to tick to be able to be involved. But we do want that to be something that can be scaled, because we are going to need people in the industry who just understand how this stuff works. And hopefully, if everything goes to plan, we'll need lots and lots of people, because this is a really, really big problem.
Yes, absolutely. So do we just follow Great Southern and see how to follow the work? Because I know that Emma's going to be working down in Tassie. I'm on the coast as well, and we've got quite a network that's on the coast that is very interested in definitely watching this space.
Yeah, so I think the best way to do that, my wife Caroline's in charge of that educational component, and so liaising with her in terms of how that might be able to be something that can be scaled to other regions is the best way forward for that.
Fantastic. Emma, have you got any questions?
Well, I guess my only curiosity was around, you've mentioned about all of these solutions having problems with them. Are there any other problems that have come about with the seaweed restoration other than the logistics? Any other concerns from, other groups that...
So there's a bunch. So, and to be honest, like a lot of them come from myself as a biogeochemist. So if you pump deep ocean water to the surface, this is something that happens naturally in certain areas around the world. Off of Peru is the most well-known area where deep ocean waters come up. They basically, I'll simplify, they hit South America and get pushed to the surface. And then you have the massive Peruvian anchovy fishery that basically lives off of those nutrients coming to the surface there. And it is absolutely astonishing and massive in scale in terms of how much grows in those locations. And there are other locations like that around the world. David Attenborough did an episode off the east coast of South Africa as well, of Southern Africa, sorry. So those activities happen in places where the environment has evolved to manage them. What we're suggesting is doing this in places where it's not naturally already happening. To give an understanding of why it's really important, why many people are looking at this as a solution, is that top 100 meters of the ocean where most of the organisms live, just below that is really nutrient poor. The biology uses up all the nutrients. Just below that 100 meters is where all the nutrients are, because they were in here, they then sink, they die, they dissolve again, there's all the nutrients. So if we can pump the nutrients just a little bit, into that 100 meter section there, we'd actually be able to produce a huge amount of production. Now, the problem with that is that below that 100 meters, there's a whole bunch of other stuff. So it's actually quite high in carbon dioxide. It's quite high in a whole bunch of other greenhouse gases. And so if we pump them to the surface, is that actually going to do more harm than good in terms of what we're doing? And we don't really know. So there was a big study that was done recently. One of the leads on that was Professor Phil Boyd. He's here at the Institute of Marine and Antarctic Studies at UTAS. And what they basically found is we just don't know enough about how the biogeochemical cycling will be affected to be able to safely pump deep water to the surface and know what's going to happen. And so we do need to do a whole bunch of pilot studies on doing that. So that's a good example of some of the problems, but you can see how all of a sudden it's getting quite boring to actually talk about. It's like, oh, this is complicated and the scientists fighting with scientists. It's not really that fun. And that's one of the problems, is you're kind of stepping away from the simplicity of the story to actually going into the complexity of the detail. One of the ways to get around that is actually we know that seaweeds can actually be sunk down into that high nutrient zone. They actually love soaking up the nutrients in the dark, and then you bring them back to the surface, and then they use the nutrients to grow when they're in the light. So now you're not moving the nutrients to the surface, you're moving the plants down. And this is actually what happens in the open ocean. the microalgae actually have buoyancy control, and they go to the surface during the day, then they go down to where there's more nutrients at night, suck up some nutrients, and they come back. So that's a really natural cycle that happens in the ocean already. And so we'd just be actually kind of emulating that with much broader scale organisms. But then you have the engineering solutions problems. Then you have to be able to figure out something that can be lowered and raised every day in 20-meter swells without getting destroyed. So there's a whole bunch of issues with doing all of that, but it's a way of getting around some of those problems. And each of those other solutions that I put forward have similar kinds of sort of biogeochemical issues. Are we going to create a bigger problem by trying to solve the problem in the atmosphere in a particular way? And that's one of the biggest issues we've got. Like how effective are each of these solutions? Do you, and I think as Phil Boyd says, do you kind of plug the whole of carbon dioxide here and then you create a massive geyser that spurts out over there that's actually even worse? And in the ocean, that's one of the problems we really need to try and pay more attention to. Does that answer the question enough, Emma?
Yes, it does. And that really kind of stemmed from when you said about putting the rock solution and changing the pH. And my initial thought was, isn't that terrible for the animals? And then I was just thinking,
So I think it's important to say there are lots, at this stage, we've reached a point that is so catastrophic for the environment that actually we need to put all the ideas on the table. We need to figure out, well, what is the outcome of us doing this? Do we take the White Cliffs of Dover in England and mine them and dump them in the ocean? Is more or less what they're kind of suggesting as one of the options. It doesn't sound very good to me. It doesn't sound like it's a really good way of going about this. However, we should be considering it. We should be sort of saying, is this something that's actually the best solution with all of the other problems that come out of each of the other solutions that we're coming up with? And so that's what I sort of, those types of discussions are things that I don't think should be had in the media. They're things that should be had by people that sort of are looking at all of these different issues together and then sort of saying, well, actually, we've looked at everything and here are the 5 things that are actually going to work with the minimum amount of additional negative outcomes. And so that's why I say we shouldn't say no right now, but we should be very careful about what it is we choose to do next. And that's another one that I just thought of that's kind of a really different type of issue is kelp reforestation projects. So one of the things that, I think it's a really fantastic thing to do. I think it's great to try and reforest these areas that we've either destroyed through harvesting or we've destroyed through increased silt runoff from the various different terrestrial farming practices, has put a whole bunch of more soil out into the ocean and has buried a whole bunch of ecosystems. How can we go about reforesting those areas that we know there used to be kelp forests or there used to be seaweed forests there? And there's lots of activity in this space in New South Wales. One of the problems is, well, are we creating a monoculture? How can we do this in a way that really encourages the diversity that we know ecosystems need in order to be resilient? And that's one of the key things that we've heard from other researchers inside IMAS and around is actually we can't just solve the problem we can't solve the problem of seaweed in the way that we've done terrestrial farming. We need to try and approach this in a different way if we really don't want to just sort of build new problems for us to solve in some ways. And that's something that we're really keen on making sure that the way we approach this is trying to approach it from, okay, how can we make it so that it becomes more like its own ecosystem? It won't be the ecosystem that was there because we've destroyed that. But we might be able to produce a productive system that is there, that now is really good for other things that are looking for a new home.
Brilliant. All right, well, it looks like there's no more questions in the chat. I could sit here and talk about this till the cows come home, so I won't. I know we've all given You've been very generous with your time, and we're very, very appreciative. So many nuggets of wise advice in there. We will be we've got this session recorded, so it will be going up on our YouTube channel, and I'll also be posting some little snippets of your wisdom throughout our socials over the next week or so, because I thought this was an incredibly informative session, and also really just insightful for young people coming through, to be part of the solution. Where are the jobs of the future, and how can we marry our values with what we want to do for our career? So important for young people coming through.
I think, if there were the three things that I'd say that people are going to need moving into the future, it's you need to be good at telling stories. So be good at writing. It does really matter. I used to hate writing. I had to learn how to get good at it in order to tell my stories. You need to be good at mathematics. It just opens up so many doors if you're the person that can do that. And computer programming is a really big one. A lot of the solutions are going to be using robots to go out and do most of the hard work for us moving forward, and someone's going to have to be in charge of making sure they do the right thing. So those are the three big things that have become sort of the core base of what the jobs of the future are going to be. In terms of that kind of technical skills that you learn at school, the things that get you a job are being nice and being empathetic. Nobody cares if you're not the best programmer in the world if you're really nice and you just help people with the solution. And I think it's just not said enough. It's like people don't want to work with a nasty person. They want to work with someone who's really nice and is trying to help the team solve that problem together. And that will get you so much further than all the other technical skills. But you have to practice being nice. You have to practice being nice when times are hard. When you're hungry and thirsty and you haven't had any sleep. So I think that in terms of that sort of jobs of the future, there's the technical stuff, but then there's the soft skills that are really, really important to recognize as valuable, and recognize if you're that nice person who gets picked on at school, it's like, that's all right, it's coming. Everyone will want to work with you later on.
Brilliant. Absolute gold. All right. On that note, what a way to end. Awesome stuff. Thank you so much for your time, Dr. Tom. Thank you so much, everybody, for giving up your Marine Science Monday for October we're in. Next session is going to be on turtles, which is on 5th of November. So our speaker, Dr. Kate, will be talking about turtle care up in the Sunshine Coast. So do join us for that. As I said, this session's recorded. It'll be up on YouTube. If you want to share it with your friends, share it far and wide. It's all about making marine science more accessible to everybody. So thank you so much, everybody. Go and have a lovely evening, and we'll see you soon.
Hey, everyone.